Okay, hi guys. Welcome back to our finite element analysis tutorial, and this will be the video of continuation on our um, optimization tutorial. And yeah, so in the last video, you can see that I have simulated this metal uh, holder. Uh, and this jig holder is then attached, for example, on a wall, and the force acting on the surface is 100 Newton, and we need to do the connection simulation for these uh, two components and select the lines here as our uh, rigid body, and then continue for the remaining lines so that we can simulate both parts in tandem, in connection, and as a one part. And then after the simulation, we can see what would happen when the load is acting on this body, and what will happen to this material due to bending moment. Okay, so after we have define all the six lines, and you can also define all the six rigid body and with rigid element, and we choose similarly for all the six lines. Okay, so we have all the six rigid element. I want to hide it so that it won't block our view in our next process, which is to run the solver. And yeah, let's do the calculation. So no singularity, so I will say our calculation is correct, and we have under static case solution, one versus stress, and the value is about 2.99 times power 7, and still lesser than the Young modulus of aluminum, that is 7 times 10 power 10. So we'll look at the displacement vector here, and we have maximum value of 0.583. Okay, so what now? I can also activate both and put it side by side so that we have this translational displacement here and form a stress on the left hand side, and you can see together uh, what it looks like. So on the right side is the translational displacement due to bending, and the stress distribution due to bending, and the critical value would happen at this corner, at this edge, and yeah, something will also actually happen here but it's not showing. um, Maybe I have create a rigid body, and does actually react with the, yes, with the element, another element, and want to see uh, metal, the material connection, can run this. I can also hide all the white element here, the sim welding element, so we can see our connection better. Okay, so I want to go in, and yeah, so you see all the elements between these two different materials are connected. So that means that our simulation is correct. Okay, I want to increase the amplitude, the scaling factor. We can also do that, and then click OK, and yeah, see the exaggeration mode at 44 times magnitude. Okay, and then okay, so we have our result here, and after the simulation, now we want to go to optimization. So before we start the optimization, what is optimization? Optimization is the um, methods of optimizing the simulation model that is solving the equation to the optimum value that we have targeted. For example, in this case, I would like to uh, set a target, set an optimum displacement at, let's say, zero point 0.2. So I will ask the computer to solve the mathematical equations in order to limit our translational displacement and delta L to not more than zero point 0.2. It can be reached 0 0.2 or maybe lesser or not more than 0.2. Okay, so if we set a target value, we should try to converge during the calculation and reach the value that we have set as our target value. So before we proceed with the uh, convergence calculation, we will need to first enable the sensor. So inside our default sensor here, you will only have energy. So what we need to have next would be create a global sensor for three things. Maybe for the first we can choose only maximum displacement. So if you want to do all the three, the another two would be the maximum volumetric stress, and the last one would be the mass. So why we need to enable these three? So these three are the things that people always set as our optimum value for the optimization. Okay, so once the optimization is calculated, sorry, the optimization is being solved, there are actually several optimization target in finite element analysis. For example, the size, length, shape, and topology. Topology is to deal with the surface uh, of the material of the part. So in this case, we'll set the length. This is the deflection length here. So from the original value, 0 at 0 in this case, and then the value, the distance between the top most of this part to this position now is about 0.583 millimeter. So okay, and it also can be seen here. If, for example, your in your Catia, you don't have this value enabled, you should go to Tools, Options, and go to Parameter and Measure. And the knowledge, we have to select with value. Tick the with value, and then just click OK. So we get this to enable the value enable here. Okay, next we go straight away to the optimization. You should go to Start, Knowledgeware, and then click on Product Engineering Optimizer. So it will be suddenly changed to this environment, and you can then search for this bullseye or target symbol and click on the optimization window will have open. And the problem, when we start with problem first, we want to set to target value. So we have several selection here. Minimization, if you don't know the target value yet, so you can ask Catia to calculate up to the minimization that is the minimum value as possible, and also maximization, the maximum value as possible. Or if you only have your value, you can click on target value. Next, you have to click select to choose the optimized parameter. So in this case, the sensor is shown here. So this is where the sensor element is important. So we would like to click on the maximum displacement, click on OK, and click on the edit list. Sorry, before that, I have to set my target value. So let's say I want to have maximum deflection of 0.1 while maintaining the force at 100 Newton, and yeah, and that's it. So how about click on the edit list to select what kind of um, um, target element to be reduced up to 0.1. So in this case, we have a lot of elements here. So we have to choose which one. So we have, if I scroll down here, we have distributed force, sim welding, tetrahedron, the elements, and then my um, aluminium data. Next would be the remove body. So all from starting from remove downward will not be used in our optimization. So the one that is important now will be the length, uh, the radius, and the thick thin body. So let's say, all right. So we have these two values here, length 13 and length 14, which has a value of 2.54 millimeter, and these value are actually the thickness of this C channel. So it is 0.1 inches, 0.1 inch, the thickness of this C channel. So yeah, I set that as our target value. That should be modified if I want to not target value. My target optimize shape. Uh, if I want to set that my displacement would not be more than 0.1. So that is my target now. So after we have set that, we can just move forward to termination criteria, and these three will consume your calculation. So maybe we have to reduce it to lesser value so that we can save some time for this tutorial. And then disable the optimization data, disable the save optimization data. And for run behavior, we click on this visualization update and untick the disconnect undo lock. Okay, so next would be um, okay, I put this a little bit in the middle so that we can see what will happen to this value, to this uh, design, and also the value here. Okay, next I'll click on run optimization and just wait for the data to be optimized. Uh, so we wait until the calculation converge and we get the value that we targeted. So see, there's changes here already. The maximum displacement will reduce to not more than 0.2 or equals to 0.2, or the maximum value that the calculation can reach. So with the maximum number of updates only 10 and the target value 0.1, it can only converge up to 0.277 millimeter. If you see that something is happening now, you will see that yeah, um, it changes our thickness, and this thickness is too thick now. And this is an example of how it suggests us to do. And it suggests us to have a model, to redesign the model after we set the target, the thickness as our target, with the maximum displacement of about 0.1, and it can only converge up to 0.248. If I click on OK, I will accept the design. If I don't want the design, I can just click cancel. So come back to the original length, thickness of 0.1 inch or 2.45 millimeter. Yeah, if I want to change the optimization target, for example, I still want to have a target value, but this time I still want to have the maximum displacement, but this time for the free parameters will not be the length 13 and 14 anymore, which is the thickness, not the thickness anymore. I don't want that thickness anymore. So I want to change to length, the first limit length, which is the original length of this C channel, which is 200 millimeter. So what will happen if I want to reduce the displacement from 0.583 and the target value is 0.1? Yeah, let's see what would happen now. I reduce this to save some space and click on run optimization. Okay, so you can see displacement reduce even better, and you can also see something happen here. Yeah, So if you could already gas. So actually, yeah, you see, something happened here, and it can reach up to zero point 0.1, and the value maximum will be 0.104. What will happen here now is you can see the C channel becomes shorter, but the thickness remain the same. So this is the suggestion by Catia. So in order to reduce the displacement up to only maximum zero point 0.1, while the load for bending is still remain the same, or 100 Newton or 10 kilogram, for example. Yeah, it says that we should reduce the length, because this is correct. If you look at the tensile stress or the bending moment equation, the length, the original length of the material of the part is directly proportional to the displacement, and delta L is proportional to L. So in order to reduce delta L, you should also reduce the original length. So this is what is suggested by Catia. And if you yeah, if you want to accept this design, I can just click OK. So it will automatically accept this model, and also change your um, model, original model, and then you can also save it by under the same file, or you can save it under different file, so that you can use the original length later on. So if I click OK, so this is our new model now. Okay, you see the distance, the length of this change. If I want to show you the new length, now would be 116 millimeter only. 160 millimeter only instead of 200. So this is one way to do optimization, and ask Katia to help us to suggest um, what should I do in order to reduce my, for example, displacement, or vomissor stress, uh, and what the new design should look like. Okay, it will not add more elements. It will not create, for example, stiffener or whatever. But the one that you can set is the length or the shape that is already from your original part. Okay, so with that, I think we should say goodbye.